Welcome dear students. This is second part of our week number 9 of the course Advanced Algorithm Analysis. In today's lecture, in the first half of this lecture, we talked about the quicksort algorithm. Let me revise what we have studied in the first half of this lecture. We started from the quicksort, how it works. Then we compare it with the merge sort algorithm. We saw the differences between the quicksort and merge sort algorithm. The main differences were like in the steps. For example, in the merge sort algorithm, actually the things happened in the merge step, while in the quicksort algorithm, the actual things happen in the divide step. Similarly, the running time is different. The running time of quicksort algorithm in worst case is n square, which is same as that of the insertion sort and the selection sort, while in case of the merge sort, the worst case running time is n log n. Similarly, we saw that quicksort is efficient in terms of memory. For example, the reason is that the quicksort algorithm is an in-place algorithm. It does not require extra memory, extra array for sorting the data, while the merge sort requires. And also the last difference was that the merge sort algorithm actually works from bottom to up in the recursive tree, while the quicksort, the things happen from top to bottom approach. We see the basic idea of quicksort algorithm that is actually based on the selection of the pivot. Pivot is a value that we select, and then on the base of that selected value we decide whether the remaining elements, the remaining keys are going to be on the left hand side of the pivot or on the right hand side. How to select the pivot? There are 4 different strategies, 4 different options that are available. You can select the first element as a pivot, either the last element of the array as a pivot. You can select the pivot randomly, and also you can select the medium of the given elements to work as a pivot. Then we saw how the quicksort algorithm actually works, how it sort out the data, how it make the comparison, how it make the sweeps. We started from an abstract level example where we saw the things from a bird's eye view, how it actually sort out the data, how it select the pivot. In these examples, we considered that the pivot is the last element. Okay, so based on that, we then see how the algorithm works, and then in the second example we consider the array and we apply the tactics of the merge of the quicksort algorithm on the data. Then we saw the pseudocode of this algorithm, and we saw a practical dry run of the example by using the quicksort algorithm pseudocode. Now it's time to analyze the worst case analysis of the quicksort algorithm and the best case. So let's assume that we choose a pivot element in such a way that it give us the most unbalanced partition possible. Remember, the selection of pivot is important. If you select the first element to be the pivot, then there is a problem which may occur. And the problem is that if the array is already sorted in sorted form, then in that case the partition is not even. All the elements are going to be on one side, while the second half of the division will contain no elements, 0 elements. This situation is called the worst case. Okay, so let's assume that our worst case is like this. We choose a pivot element in such a way that it will give us the most unbalanced partition. Most unbalanced partition mean that almost all the element will occupy one side of the array, subarray, and the second half will be empty, will contain 0 elements. So in particular, suppose that the pivot chosen by the partition function is always the smallest or the largest element in the array. What does it mean? If the array is in ascending order and you select the first element to be the pivot, then all the elements will automatically go to the right hand side of the pivot. That is the worst case. Or vice versa. For example, if the array is in descending order and all the elements, the pivot is the largest element and all the elements are less than the pivot, then all the elements will occupy the left hand side of the array, of the pivot. Okay, so that is the worst case also, which means that one of the partition will contain no elements and the other partition will contain n minus 1 element. Why n minus 1 element? Because one element has been considered to be the pivot. So minus pivot will give us n minus 1 element on the second half. So the recursive call will be on sub arrays of of size 0 and size n1. Like you have two sub arrays. One sub array has 0 element and the other sub array has n minus 1 element. Why minus 1? Because one element serves as a pivot. So in this case, if you call the recursive algorithm, recursive function, so it will be on 0 and n minus 1. So as we saw in the merge sort algorithm, the time for a given recursive call on n element sub array is theta n. We know it from the merge sort. If you want to sort n elements, then the recursive call running time is theta n. In merge sort, that was the time for merging. Remember, the main operation, the main things in the merge sort algorithm actually happens in the merge step. So the time is for merging. But in quicksort, it's the time for partition because the main things happen in the divide step. So when quicksort always has the most unbalanced partition possible, then the original call will take n time. This is the original call. The first time that you select the pivot, the first time when you divide the array, it will take n time. And this is the divide time. Then after that, the recursive call, now we have, remember it is uneven partition. So on one side we have 0 elements and on the other side we have n minus 1 element. So for the second call, the second recursive call on n minus 1 elements, it will take how much time? N minus 1. And we know it from merge sort as well. It will take n minus 1. Then on the second call, n minus 2 elements. Okay, because now one more element has been selected as a pivot, so n minus 2. And it will take n minus 2 time. And then n minus 3 and so on up to 2 elements. And then finally we will have one element, because one element will be selected as a pivot, so one element will remain and the running time here is 1. So this is actually a tree of the sub problem sizes with their partition times, how much time each of the statement will be executed. You can also say like that. Okay, let me share one thing with you. In some algorithm analysis books or on some articles, you will see that the running time here is considered to be 0 in some cases. So if we consider 0 here, that is the runtime at the last step, then in that case you have to subtract minus 1 from the equation, from this equation, n into n minus 1. Here you have to put minus 1 as well. But in our case, we consider it to be 1, so we do not need to subtract minus 1 from here. Okay, to find the time complexity, to find the worst case running time of the quicksort algorithm, we have to add these running time of individual sub arrays. So it is simple: n plus n minus 1 plus n minus 2 plus n minus 3 and so on, plus 2 and then plus 1. So it will give you an equation like this. And we know from mathematical summations that we can write it like this: n into n minus 1 divided by 2. Now this is our final running time of the worst case of quicksort algorithm. Apply the rules. What are the rules? Any leading constants, for example 1 by 2 or other things, ignore them. Once you open it will give you n square by 2, just like this, n square by 2 and minus n by 2. So the two rules are that you have to ignore the lower order terms. So here n has a power 1 and here n has a power 2. Ignore n power 1 and also ignore these leading constant, that is 1 by 2. So what remains is n square, and that is the running time of the worst case running time of the quicksort algorithm, that is O, big O n square. Okay, and we use the tree approach. You can also use the recursive approach, or other methods are also available for finding the running time or to analyze the quicksort algorithm. Different methods are available, so the tree method is the most simplest method. Now let us see the best case. Sorry, this is average case, but make the correction. It is actually best case. The average case analysis is also log n. So both have the same running time. Okay, the best case scenario. First thing is that when will the best case occur? So the best case scenario occurs when the partition are as evenly balanced as possible. The worst case was happened when the partition was unbalancedly occurs, unbalanced partition, and the best case will happen when the partition are evenly balanced. That is, their sizes on either side of the pivot element are either equal or have a size difference of 1. Why a size difference of 1? Let us see. Actually, for best case analysis, we have two possibilities. Possibility number 1 is that when the sizes of sublist on either side of the pivot becomes equal, and that is possible when we have odd number of elements and the pivot is right in the middle after partition, and each element will have n minus 1 by 2 element. Things become complicated. Let us see how it works. Suppose this is case number 1. Okay, this is case number 1. Suppose you have odd numbers. Odd numbers mean 1, 3, 5. So here we have 5 elements and the pivot is in the middle. This is our pivot. So in this case we have equal number of elements on both the sides, and this is possible only when the given array has odd number of elements, 1, 3, 5, 7 and so on. So in first case, the list will have equal, both the sublist will have equal number of elements, and that is possible when the given array has odd number of elements and the pivot is in the right of this array. In this case, each partition will have n minus 1 divided by 2 elements. In this case, n is 5. So 5 minus 1 divided by 2. That is 4 divided by 2, and that is equal to 2. So we have 2 elements on the left hand side and 2 elements on the right hand side. So let me repeat. For the best case, we have two possibilities. Possibility number 1, when the list has odd numbers. In that case, the pivot will become the middle element and both sides will contain equal number of elements, and we can generally write it that each side will have n minus 1 divided by 2 elements, and we can prove it like this. That is the first possibility. The second possibility is that there is a difference of 1 between the two sublists on either side of the pivot. Okay, so it will happen if the sub array has even numbers. Let us consider the second possibility. Now the array has equal numbers. Sorry, the array has even numbers of element like this. How many elements do we have here? 1, 2, 3, 4, 5, 6. Suppose our pivot is 6. Greater elements are on the right hand side, while element less than are on the left hand side. This is pivot. Okay, so this is the even case. In this case, one of the side, either left or right, will contain one more element. So in this case, the left hand side has one more element. For example, here we have a total number of 2 elements on the right hand side, but on the left hand side we have a total of 3 elements. So this is the second possibility, that the size is there is going to be a difference of 1 between the two sublists if the given array has even number. So it means that on partition, one partition will contain n by 2 elements, while the other partition will contain n by 2 minus 1 element. Let us prove. Here n is 6. So 6 by 2 is equal to 3. And here n by 2 is actually 3 minus 1. So one side has 2 elements and the other side will have 3 elements. And you can see on one side we have 3 elements, on other side we have 2 elements. In some cases maybe you got 2 elements here and maybe you got 3 elements on this hand side. It depends on the situation. But that is the best case analysis. And the two cases, the two possibilities. One, when the given array has odd number, in that case we will get n minus 1 by 2 elements on either side. And the second possibility is when the given array has even number. In that case, one side will contain n by 2 element and the second half will contain n by 2 minus 1 elements. Now let us see the analysis. So the analysis is same. First we have the list and the total number of elements are n, and there is n divided by 2. Okay, remember the total number of element is n by 2. So after that, after first recursive call, we will get n by 2 element on one side and n by 2 element on the other side. Why we put this sign less than or equal to on both sides? What is the rule of less than or equal to sign here? So actually each partition, we don't know whether this side has n by 2 elements. Like we have two possibilities as I just mentioned. One side will contain n by 2 elements and the other side will contain n by 2 minus 1 element. So instead of writing these two, we have a general term which is like this: less than or equal to n by 2, which mean at most. This is for at most. At most mean n by 2 or less than n by 2. So it could be n by 2 or it could be n by 2 minus 1. It could be anything, this or this. Okay, because on one side we have n by 2, but on the other side we have n by 2 minus 1. So we can write generally these two equations like this: less than or equal to n by 2, which is read like at most n by 2, which mean n by 2 or n by 2 minus 1. So in the first recursive at the beginning we have n by 2, then we have n by 2 to the power 1, then to the power 2. Actually the to the power 2 to the power 1 means 2. So we have 2 subarrays. 2 to the power 2 means 4. So we have 4 subarrays: 1, 2, 3 and 4. 2 to the power 3 mean 8. So we have 8 subarrays. Finally we have to continue until we reach the base case, and the base case is 1, only single element. So we can write it generally like 0, 1, 2, 3 up to k. So n divided by 2 raised to the power k. If you remember the binary search analysis using tree method, so this equation can be right like this. So n divided by 2k is actually equal to 1, and we can write it like this. Simply multiply both the side by 2 raised to the power k. Here it will be cancelled, and then we will get n is equal to 2 raised to the power k. And then here you have to apply the logarithm, taking log, and remember the log is base 2. Taking log base to the base 2 on both sides, we will get things like this. Log of n is equal to log of 2 to the power k. We can write it here k, and log of 2 is equal to 1. So k is actually equal to log of n, and that is our final running time. So the best case running time of this quicksort algorithm is log n. Okay, so the time complexity is equal to the height of this tree, and that is equal to big O log n. So that is the best case as well as the average case running time of the quicksort algorithm. Okay guys, finally we have another type of algorithm which is called randomized quicksort algorithm. Did you remember the bubble sort algorithm and the enhanced version of bubble sort algorithm? Yes, so we also have an enhanced version of the quicksort algorithm. Okay, what was the problem with the selection of pivot? That if the array is already in sorted form and you want to select the first item or last item to be the pivot, then the performance will be degraded. So suppose that your worst enemy has given you an array, and he or she asks you to sort it with quicksort, and the condition is that you always choose the rightmost element in each sub-array as the pivot, mean the last element, and has arranged the array in a way that always get the worst case unpartitioned split, as we just saw. So he or she is your enemy. He wants you to sort an array by using quicksort, and the condition is that you always have to select the last element to become the pivot, and the array is in sorted form. So what will you do? How can you foil your enemy? You could not necessarily choose the rightmost element in each sub array to facilitate your work. Okay, but instead you want to randomly choose an element in the subarray and use that element as a pivot. But remember that the partition function assume the condition is that the pivot is going to be the rightmost element of the subarray. That is the condition. So how you will solve this problem? No problem, there is a solution. The solution is very simple. You have to swap the element that you choose as the pivot with the rightmost element or with the last element, and then do the partition as before. So unless your enemy knows how you choose random location in the sub array, you win. You will get the optimum performance out of the quicksort. This is the concept of randomized quicksort, where we randomly select a value and we swap it with the element at the last location. So if you select the last element to be your pivot, and then you select another value randomly, and then you swap them out with one another, the concept is that of the concept of the randomized quicksort. But things doesn't end here. There is a general concept that we actually swap a random value with the element at the last location, okay, in order to enhance the performance, especially the worst case performance of the quicksort algorithm. And you will see that by using randomized quicksort algorithm, we actually get n log n in the worst case. Why? Because our pivot is either the first element or it is the last element. as in case of the previous quicksort algorithm. But here, after selection of the pivot, either the first element or the last element, we swap it with a random element, and this make things change. By using this technique, we will get n log n running time even in the worst case. So that is possible with the help of randomized quicksort algorithm. Now, something for you. Assignment number 3. Explore the concept of randomized quicksort algorithm. The instructions are similar to the previous instructions. First, you have to provide a background, a context to the randomized quicksort algorithm. You can write something about the quicksort algorithm and then why we need the randomized quicksort algorithm, what is the improvement made in the randomized quicksort algorithm, and things like that. So provide theoretical background. Then in order to explain the randomized quicksort algorithm, you have to provide the theoretical aspects as well as examples, the algorithm pseudocode or flowchart or English statements, and if possible you can give a dry run to an example, and also the analysis, especially the worst case analysis of the randomized quicksort algorithm, which is n log n. So I'm interested in that. The deadline for submission of this assignment is next year. So you have 1 year to complete your assignment. Relax mode. Total number of pages 5 to 10. That is up to you. Minimum then 5 or greater than 5 will have an effect on the assignment. And the medium of submission is online through Google Classroom. I will post the assignment there. You will be notified once the assignment is posted there, and then you have to submit it by using Google Classroom. Remember, I prefer to receive the assignments only in PDF format. If you send me an assignment in MS Word docx format, so I will not be able to properly guess the formatting because I am using LibreOffice and formatting issues are there. So to make things tight, to keep things tight, you have to you can write your assignment in the MS Word and then convert it into the PDF, and after conversion you can send the PDF, the final version of the assignment, to me. So this was about quicksort algorithm. We started with the general introduction, and I'm sure we have achieved the objectives from this lecture. Now you are able to explain the concept of quicksort, how it works, what is the algorithm of quicksort, how the algorithm actually select the pivot, and how the elements are swapped and compared with one another in order to get the final sequence. And finally you learn about the analysis of the quicksort algorithm, and we concluded that the worst case analysis is n square, while the average case and best case analysis is equal to n log n. That is the same of merge sort. Okay, and that is an efficient sorting algorithm, especially if the list if the list contain huge number of elements. So that is a better approach to sort out the data. Okay, so this was about today's lecture. See you in another video. Till then, goodbye. Take care.